Okay, I started recording. All right. So now today's lecture, we're going to actually look at a related topic. We have actually studied different kinds of trees. We started with binary trees, and then we introduced, binary search tree, and that's one of the useful binary trees that we can use for doing searches in a very efficient way. So, and then there are many other trees. And then one of the things about the binary search tree is it doesn't have a mechanism to keep the height of the tree low, like what we'll call balanced, so that, sort of if you any node in the tree, your left subtree and the right subtree, they are roughly the same height, or at most, you know, has a difference of a one level, right? That would be a pretty balanced tree. And the advantage of this, as we see the running time for the operations on the tree, on a binary tree or other type of tree, is has a lot to do with the height of the tree. So essentially, the the shorter the tree is, and essentially the more efficient your tree traversal or your whatever operations you do is going to be that much more efficient. So that's why it's desirable to have so-called balanced trees. So there are many different kinds of balanced trees, but I'm gonna just kind of introduce you to two types of a common balanced trees. And they have, again, as all the data structures we introduced this course, they actually have a real world applications. They're not just theoretical discussion, they're actually very much useful, okay? All right. Now, so balanced trees are, surprisingly versatile. They are used in many different places. Maybe you're not aware, perhaps after you study this course, now you're gonna be a little more curious when you use some library, and you may wanna look into, do a little research, see what's behind the scene. As an example, the hash table that we introduced last lecture, and one of the ways to solve the collision problem is by chaining. You could just use a linked list. That's one of the simple ways. And in fact, another alternative instead of linked list, you get in terms of the search uh, running time, it can be a big O of n, right, for that linked list. Now, an improvement could be using a balanced tree for the collision handling in a hash table. And in fact, that is actually what's being used in the hash map implementation in Java, okay, which is a hash table implementation. So, again, what the implementers of different libraries, what they choose to use, that's a people's call, right? So, there are, again, different language, different libraries, they're going to have different choices, and people use different data structures and different algorithms. Yeah, there's a lot of things out there. So if you're curious, once you have taken this course, you should be more curious about what is the data structure that's being used behind this library you're using. Don't just look at the interface, now you know how to use it, but be a little more curious to see, look into what is actually behind in your particular implementation, which may be different between, the compiler you use on a Mac or versus on Windows. There's can be different implementation depending on the compiler of your choice. So I just want to give a little, overall concept about, these data structures. Actually, they are everywhere. So as a listener here was, I was talking about different languages are going to actually have, typically they will have some kind of balance tree that's being used internally, although it's not going to be a, sort of at the standard level to say, hey, this here is a balance tree, and then go ahead and use that tree. Typically, it's going to be just implementation details. Okay, it's, interface presented to you is going to be, familiar standard, a couple of functions that you're going to use to interact with that data structure, or, a container. Like in C++, right, this is standard map, which is a ordered map. If you want an unordered map, there's an unordered map, which is actually hash table. And this map, it typically the way it's implemented, and this is not really in the standard. The standard doesn't say you have to implement this as a tree, right? It doesn't say that. But in reality, most of the compilers, the implementation of a C++ standard is going to use some sort of balanced tree if you really dig into that. So this is just an example. The map and the set, they are implemented as some kind of a balanced tree. As I said, there's different kinds of balanced trees. Today we're going to look into red-black tree and also B tree. And there's other balanced trees such as AVL tree, and there's just all kinds out there. You know, because as I said, this is the area of very active research, and there's people just want to come up with the better things all the time, which can be more complex. But usually what you study in this course gives you a good foundation, and there are other things they're going to be. There are sort of variations, some kind of minor improvement, not so dramatic, but you know, at least you'll get a hang of how things are going. So Java, you know, if you have studied this language, you're gonna know there are some of the classes in the standard library called tree map, tree set. You may have not used this much, but these classes are actually, I mean, as the name indicates, right, this is how Java does things. Those are actually implemented as a balanced trees as well. And exactly what kind of balanced tree, as I said, when it comes to engineering, come up with a really optimal solution in the real world that's battle tested. Typically, is not just a simple exercise of a academic research, you know, like implementing what we're going to discuss, sort of the core of the algorithm. Typically, there's all kinds of optimization to kind of try to get the last ounce of performance out of it. So there's sort of engineering tooling, you know, around things that's going to make it a little more complicated if you dig into the source code, if it's open source. I mean, in fact, there is OpenJDK. You can look into that if you're curious about it. Haskell is another programming language, and then so in that data.map library also, that's also a tree. So just as an example, there's many other programming languages that all have used some kind of balanced tree in their library typically, because this is very useful. All right, so we're gonna actually first take a review this BST, the binary search tree, as I mentioned. That's what we already studied one of the earlier weeks. Binary search tree is a binary tree with a couple of properties. So typically, if it's just a random tree, it's not that useful. We always want to put some constraints on the tree, maintain some kind of property. Now remember heap? Heap is a tree, right? Now heap by itself may not be balanced. So the real world application may not be used the plain heap that we explained, but it's gonna, you know, use some variation of it, but the idea is the same. But typically want to have this, keep this balance so that the height, keep this height as small as possible. Now, binary search tree essentially have simple properties. You know, each node stores a key. And of course, you can always have auxiliary information like satellite data, right? For the purpose of discussing data structures, we typically just ignore the satellite data, but in real world applications, you always carry information because you're not just dealing with the keys. Of course, you're dealing with objects. So, but you know, it's the same thing because we're not operating on the auxiliary information, so they just carry it around. But the primary thing is the key. And the key of every node in the BST is strictly greater than all the keys to its left and strictly smaller than all the keys to its right. So it's kind of a partially ordered, okay? Sort of the parent is in the middle between the left and the right, okay? But it doesn't really enforce a exactly strict ordering, but it's some sort of ordering. So that is a property that it maintains. So the height of a binary search tree is the length of the longest path from the root to a leaf, okay? So from all the root to the leaf, all the path, the longest is the height of the tree, right? So you may have certain leaves that are sort of lower, but then you know the longest is defined as the height. A tree with one node has a height 0. It's just, you know, by the definition. There's really zero path, that's height 0. So for example, right, this tree, which will have a height, if you look at the longest path, 1, 2, 3, easy to see. Of course, if you want to compute it, right, in an algorithm, then you would have to do some traversal to figure it out. And we have looked into that before in that implementation. So how do we insert a node into a BST? Okay, let's say I want to insert this value 166. So 166, well, to insert this value, obviously you first start with finding where you need to insert it, right? You basically compare, right? We have studied this before, this is a review. And so you're gonna look starting from the roots, 166 is greater than this, so you look to the right, okay? Because that property, remember, of the BST. Now you've seen this 271, and which is greater than the node, the value you want to insert. So we'll look to the left. And 161 is less than what the value we're trying to insert. And then we're gonna just put, right now it has no more, this is the leaf node, right? So we're gonna just attach this value to this, to the right, okay? So we're gonna just, move her a little bit more because we have seen this. Now look, okay, let's take a look at the deletion situation, okay? So if the node has no children, just remove it, right? So here's an example. This 40. Hold on. Actually, we say when delete 166. Actually, that's yeah. So that's just hold on a second. Oh, so first thing we're gonna look at is 57. Let's say we're gonna delete. Okay, we delete 57. Simply just delete is a leaf node. Now, if we want to delete something that has children, like 96, we'll have to just basically remove that and then replace it with its child. You have a single child, okay? And then if we are going to delete something has 2 children, and then we actually have to rotate the tree. As you see, in this case, we're actually deleting, let's see what we're deleting, 137. Let's say we want to delete this root node. So we'll remove it, but we have to find the in-order successor. The in-order successor is actually 161. So the value right after 137, this is the in-order successor, the next node. After 137, that would be 161. And so that will be replacing that root node. And then this original node will replace that one, it moved up. Okay, so that's kind of the gist of that. We have, look at the algorithm before, just a little review. And so as you see, that this tree manipulation is structural. When you insert or delete, you want to maintain the structure in a way that the definition of the tree that comes with the constraints are maintained, or those properties are maintained. For BST, want to make sure that any node, the parent node, that value is less than all the values in the left, and well, greater than all the values in the left and less than all the values to the right. So that's kind of one of the core properties to maintain. And then, as we know, the operations, most operations on this tree is basically big O of H, which is the height of the tree. So that's why it's important to get the tree as short as possible. Okay. Now, as we know, in the worst case situation, you have like basically a linked list, right? Every node except the leaf node has a one child only. So that would not be a good situation. That's why it's good to keep the tree balanced, keep that small, so you're gonna have a better performance. That's what it's about. So let's look at one way to do this. It's called red-black trees. Red-black tree is a tree that has a couple of properties, right? So it's using 2 colors. It's trying to color every node. Every node can be either black or red. And then we're gonna say the root node is black. And also there's no red node has a red child, okay? Means that if you have a red node, it cannot have a red child. So you cannot have two red nodes right next to each other as a parent-child relationship. So that's one constraint. Now that constraint is important, and that's actually what you know, we'll see why actually just in a bit. And then there's another property. This is property is actually what's sort of constraining, well, actually combined with the previous property, two together, that's what keeping the tree balanced. And so every root to null path, now the null root to null, just imagine if this has a null children, right? Let's say have a null left child, null right child. And so from the root to the null path, it will go through the same number of black nodes for every such path. Like for example, from here to this path, we have 2 black nodes. And then from here to this one, we'll also have 2 black nodes. And then to this one, this leaf here, and then we have also just 2 black nodes, okay? So that is sort of the one of the main properties to keep the tree balanced. Just this property alone is insufficient, but also one have the constraint that a red node cannot have a red child, okay? So if you see a red here, and then the children will have to be black, okay? All right. So in fact, you could have a whole tree that's all just black nodes. That is fine. This is actually an example of a perfect tree, right? Perfect tree, and this is a perfect tree where it has, you know, every node except the leaf that has 2 nodes, and they all filled, okay? So this is sort of a so-called a perfect tree example, perfect binary tree, in fact. And they're all black. This would be fine. This is an example of red-black tree, and this satisfies all the conditions here, right? Every path, you have 3 black nodes, right? Now, we can easily prove it, but we're also going to see an alternative way of looking at that is that any red-black tree with n nodes, it has a height of a big O of log of n. So let's say you have this 1, 2, 3, 4, 5, 6, 7 nodes. Okay? So the height in this case, we'll see the height is actually 2. So anyway, the height is actually in this big O notation is a log of n. Now, that's a nice property, by the way. It's pretty much as good as you can get when it comes to trees. And we know the worst situation, like extremely unbalanced tree would be a linked list. And then that tree has a height of a n-1, right? You have all n nodes, you know, lined up, parent to child relationship. So now, as we know, the lookups, at most, you're going to look up from the root to a leaf, and then it takes time of a big O of log of n, which is the height of the tree. Now, so how do we mutate the trees? Essentially, how do we insert and delete? Suppose we want to insert this node, you know, 13. And we know this is the position because by the value of now, you know, keep in mind though, it still maintains that property where the parent is in between the left and the right, okay? Like the binary search tree. So 13, you know, we could have put it over here. This is the position. And how do we mark the color so that it maintains the property of the coloring, right? So, and that's just an example here. And then, so now here's another thing also, how do we delete, right? Essentially, let's say 31, how do we delete, right? We delete it, and then this will be replaced by one of his children. And suppose it's gonna be like this, okay? So again, we know by this basic example, this is fine. This still maintains that property. See, 2 blacks, 2 blacks, and 2 blacks. So we're going to look into different cases where this mutation can happen on a red-black trees. Now, the thing about this though is, okay, after the insertion or deletion, typically we can just locally modify the tree in a big O of log of n time to fix up the properties, right? Essentially like rebalance it. However, there are actually a lot of cases to consider because now not only the structure of the tree we have to consider, but also the coloring of the nodes we have to consider. So it can be a lot of cases to handle when it comes to implementation. And they're not very trivial. So the idea here is, okay, we can make it work. And in fact, you can look, you easily find implementation online. You'll see how that's done. It may be difficult to figure out what are these cases are. I mean, if you try to remember, it will be hard to remember. And there's an alternative way of doing it. And we're going to see what the alternative way, we're going to draw an analogy, well, actually the connection between red-black tree with a different kind of data structure, which is called the B trees. Now, B tree is a different data structure, but we'll see there's a connection with the red-black tree also. Now, what are the B trees? B trees is a generalization of a binary search tree. In binary search tree, right, every node contains a single key, okay? That's the binary search tree. Now, imagine if you have like millions of keys, then you could have potentially have a really, tall tree. And then if the tree is tall, the search or operations are not gonna be very efficient, right? You're gonna do a lot of hops, so to speak, when you traverse the tree. So what you do is, in this case here, that's in the case of binary search tree, you're basically splitting. Let's say, this tree, you have a left child and right child, you're splitting the values or the key space. If you just think of this, the values, right? You have the values less than 2, values are greater than 2. That's kind of the idea here. And then what we're gonna do is that we wanna make the tree so compact. So we're kind of lower the height of the tree. So instead of just stuck in one key into every node, what we're gonna do, this is actually inspired by the reason that people came up with the B tree was that there's so much data, we want to build an index and want to actually store the data in a disk. We can't, efficiently put everything into the memory is not even desirable. Thinking about databases, for example, you're not going to load all your data in memory and just operate your memory purely, right? You just have too much data you cannot fit into the memory. You may have a gigabytes of data, big gigabytes of memory, but then you actually have like maybe a terabyte of data on the disk. How are you going to deal with that, right? So the idea then you build indexes using something like a B tree. Well, in reality, you use a variants and again improvements of a B tree like a B plus tree. We don't really discuss B plus tree here, but it's very similar. Again, it's just a bit of an improvement over B tree. And so when you see the idea is we're going to stuff many records onto every single node. And in fact, the way we pick the size of the node in reality would be, when we get to implementation is we probably want to pick the node size to be the size of a block. In terms of the block and when we load the file from the disk. So then, you're minimizing the read writes with the disk IO, which is slow compared to the memory operations, right? So anyway, that's just a little bit of motivation behind why we have such a thing. So now here's an example, right? You'll see every node has multiple keys and up to 4 keys here, actually 5 keys here, right? It ranges between 1 key and up to 5 keys. Now let's look at this particular node, right? So what we do is, you see it's splitting that sort of the sub range of keys into different regions, different zones. I mean, it's still, think of this, like here you have a 5, that means the child that on the left side of 5 is going to be all less than 5. And then the child that's in between 5 and 19 it's greater than 5 and less than 19, and so on, okay? So that's, if you have 3 keys in this node, you could have 4 children. So that's how this is, again, it's a generalization of the BST. Now you have a multi-way search tree, or it can be called a multi-way search tree. Now, so a B tree of order B, there's a property, a parameter here. We'll talk about, essentially, okay, how many keys we're going to fit into a node. So then we'll have a parameter here we'll talk about. And just be aware, I want to mention there's an alternative definition though. Alternative definition disorder, if you look online, or maybe some literature is going to say, well, there's an alternative definition would be that order denotes the maximum number of children of any node. That's an alternative way here. You see a slightly different way of using this order B here. And the B, again, this parameter essentially is used this way, right? So every non-root nodes have between B minus 1 and 2B minus 1 keys. And then when it essentially means that node, it has between B and 2B children, right? So B minus 1 keys, it means B children, right? So 3 keys, 4 children, okay? That's what that is. And the root has at the most 2B minus 1 keys, meaning at the most 2B children. So that's really, what this order B means here, okay? And I just know that there's an alternative definition out there, but it's the same thing. It's just your B may mean different things, but it's basically the same thing we're talking about. So B tree of order 3, this is actually a B tree of order 3, an example. Now, if it's order 3, that means we may have between 2 and 5 keys, right? So, and 2 and 5 keys. There's the 5 keys, between 2 and 5 keys. Now, this between 2 and 5 keys only applies to non-root nodes. The root could have less. In this example, we have just 1 key, okay? Now, this is another example. This is a B tree of order 7. Now, order 7 means I may have between 6 and 13 keys in each node, except the root node. Okay. Now the root node, of course, it also has to be at the most 13 keys, right? It meets the maximum constraint, but not necessarily the minimum constraint. Okay, so that's another B tree as an example here. Now here's another special case of a B tree as well. This is sort of order 2. This B tree here is perhaps one of the simplest B trees, and then we'll see this has a connection with the red black tree, right? So this tree, there's an alternative name for this. Right? It's called a 2-3-4 tree. Now 2-3-4 tree, what those numbers mean. Again, this actually comes from the alternative definition of a order B, as I mentioned. That would be the maximum number of children, if that B means that. So with a 2-3-4 tree means you may have nodes that have 2 children, 3 children, or 4 children. Okay, so you see here, you see the children number of these arrows here between 2 and 4, right? So that's what that name comes from. So that's a 2-3-4 tree. Now, because the B tree nodes can have multiple keys, now the operations, of course, means we also got to spend more work inside each node. In the basic BST, it's just a simple comparison with this 1 key, right? So now you have many keys inside, so you have to potentially have to search for the keys you're looking for. Now remember that all those keys in a single node are ordered. Now we know we have very efficient algorithm to look for things in an ordered array, right? So that would be a binary search. We have studied binary search, and the binary search is going to give you a logarithm, time complexity to search for something as efficient as you can get. So that's typically what you're going to see in the implementation. We'll be using binary search to actually find a key within a single node. And that node may have many keys. but they're ordered, okay? And then insertion deletion can be expensive. Now, because we have to rearrange the, potentially rearrange the nodes and keys, many of those keys, shuffle them around. Well, the trade-off is that this is the operation we do in memory. Compared to disk operation, this is still pretty fast, okay? Because we have so much data, on the disk. And then, so this is why the B tree is really designed to work with a large amount of data that we have to have sort of disk storage for it. Now, this comes to the hierarchy of access speeds. We know in a computer, the fastest we have are the registers, right? Inside the CPU, we have the registers. And then we may have the cache. Actually, let's take a look at this one. This is a good layering of the storage devices on a computer, typical computer. You got registers in the CPU, and then you also then have the level 1, level 2 caches. Right? In the modern CPU architecture, you have those things. Now, and you all see the speed of access. So one single operation takes this much time, a nanosecond, right? A fraction of a nanosecond in registers, but they are very expensive. We cannot just use the same technology that makes the registers, which is typically the static RAM, versus in main memory, you have a relatively cheaper material or cost of production that's called a dynamic RAM. Dynamic RAM, as we know, if you looked into this a little bit, is less efficient because that slower than that because it needs one of the reasons is it needs refresh. The value of binary value 0 to 1, they're sort of held in a capacitor and electric charge, and that needs to be sort of refreshed from time to time because they can lose, otherwise you can lose that value. And that's kind of thing with this main memory where we have this dynamic RAM technology. It's still fairly fast if you compare this with a hard disk, or as nowadays it's very common to see solid state drives. Similar solid state drive is going to be a little faster than the hard disk, but still it's orders of a magnitude slower compared to the memory, right? And so the I/O cost, in terms of algorithm, you want to work with the external storage on the disk. And so there's algorithms that, designed to work in that situation. And I remember when we talk about the merge sort is primarily useful for external sorting, where you have a huge amount of data that's on disk. Now you want to sort the data. So that's really where that comes into the merge sort is very suitable for that situation. And then of course, at the bottom of the whole hierarchy, you have the network, you have the data stored outside your computer on the network. And that is, tens of milliseconds to really long. When you get to 2000 milliseconds, it's probably going through the satellite, right? If you're going to the satellite internet, and about, you can get to that kind of latency. So the B trees obviously, try to minimize the disk I/O. That's really one of the main motivations. And as I mentioned previously, that the real world application probably will use a B+ tree, which is sort of an enhanced variant of a B tree. Okay, very much similar, just a variant of it. Yeah, that's really what this motivation of a B tree is. And now, what is the height of a B tree? Again, this analysis is fairly straightforward. I'm going to just move forward a little faster here. So the maximum height is, we'll get to this. If the B tree has an order of a B and it has a total of n nodes, then the height is log of base B of n plus 1 over 2. It can be easily, you can just every level of a tree, I mean, you will say this is the minimum number of nodes you could potentially have, and then if you put the minimum amount of keys into each node, then you get sort of a taller tree, right? If you fit more keys into each node, then you get a sort of a shorter tree. So we want to get the maximum height, so we'll kind of fit into, remember that b minus 1 is the minimum number of keys in each node, that property, right? We'll talk about the definition of that b before. So anyway, we can easily calculate, get to that number, and here, you do some mathematics here, there's a geometric series, and then you can just solve it. Not a big deal. So then the B tree of order B have a height of big O of a log of base B of n, okay? So, this is a nice property, okay? We have a very nice height. So we just, but what this tells us is B tree is a balanced tree. It has a very good height, small height. Now, searching the B tree. And searching the B tree, I mean, again, really, it's basically about, there's two operations, right? You're gonna traverse the nodes, but also you have to search the tree within each node, right? As you're navigating, thinking about the traversal on that B tree. As we know, the binary search, if you use a binary search, you're gonna get to this log of B, right? Log of a B time to actually find the key you're looking for inside that node. And then you're gonna also have to look at that many nodes. That's the height of the tree. So eventually you get to a logarithm, based on the number of nodes in the tree, complexity. So the search is pretty good. Essentially, as good as you can get in a tree. Now, B trees are actually straightforward. They are simple. We look at them, and again, yeah, now you see a lot of keys in each node, but the operations are actually relatively simple. There's only a few cases to consider. We're going to look at some examples. Now, again, let's take a look at, well, this is an example of a B equal to 3. We have nodes between 2 and 5 keys. I remember B minus 1, 2B minus 1. So this is an example tree here. And then, the trickier cases, right? The trickier cases actually is to, let's say if you insert a key into a node, this has only 2 keys, and we can certainly fit more keys, right? We can have maximum 5 keys, and you just put it into it, right? Not a big deal. Now, the trickier case comes when you want to insert a key into a node that's already full, right? So like this example, let's say we'll go back to a 2, 3, 4 tree where B equal to 2, right? If you have such a tree, let's say if you want to, here's an example. If you want to insert 3, right, into this node. Now we know the maximum keys we can have on each node is only 3. So essentially it overflows. We cannot have 4 keys in a single node. So we need to arrange this somehow to maintain the properties of the B tree, right? So what we do is we can split this into 2 and then move one of the keys in the middle to the parent. Okay. Once we've done that, okay, these 2 nodes are fine now. We no longer have a node that has more than 3 keys. But then after we've done this, and then the parent node has a similar problem now. We just keep doing it recursively. Now it goes to the root, and the root also needs to be done similarly with splits and then raise up. And in fact, as you see, this tree, we just grow this height by 1 now, because the place where we need to insert that key, it does not, it has to grow higher, basically, okay? Oh, by the way, with the B tree though, all the leaves are on the same level. That's one of the properties. I want to keep this balanced. So essentially, yeah, all the leaf nodes are at the same height, okay? So as you see, the B trees grow upward, okay? As we insert, and it's going to grow. And to insert a key into a B tree, and this is a kind of just a simple procedure that we can look at. So first you search for the key and insert the key at the last visited leaf node. And this is where you start. And if the leaf is too big, as we just saw, it contains, let's say, already, 2B keys after we insert. That's too much because you can at most have 2B minus 1 keys. Then you split, right, into 2 nodes of size B each. Then you remove the largest key of the first block. Again, you can also remove the smallest key of the second block too, right? But just be consistent either way. So let's say you remove the largest key of the first block and make it into the parent of both blocks. Now here, as you see, we're using this terminology that blocks nodes sort of interchangeably because in reality, we do want to use the block size when it comes to the disk IO, the block size that we're using for disk IO as the size that determines how many keys we should fit into a node. Okay, just be aware that why we're using sometimes we say blocks. So this operation we do, as we just saw the previous example, we recursively do that, splitting and potentially, adding one more layer. So, have a new parent, which is the new root. So that is the insertion procedure in a B tree. And the time complexity, essentially, we have the work at each level. Essentially, each node, we have to do big O of B and, that, splitting and searching work. And then we also have the, big O of log of N levels to potentially, arrange the structure. So that is, and then the total number of nodes we visit is basically big O of log of space B of N, right? Now, let me change position a little bit to have a little less noise, okay? Sorry about that. Okay. So the deletion. Now, normal deletion, if you have, the case that's a little trickier, we're going to look at this case, is that when it underflows, essentially the leaf node already has only B minus 1 keys left. That's the minimum. And now you're going to delete one of them. And so no longer satisfies the condition, right? And then what do we do? So the idea would be to steal or pull one of the keys from an adjacent node, typically its parent. And then we may also merge the nodes if they somehow become empty. We'll see some example here. So here's another 2, 3, 4 tree. Here is you see we want to we want to delete 6. We want to delete 6. Now you can't just do this just yet because you have to make the tree balanced, maintain that property of a B tree. So we may, let's say, pull that 11 from the parent, and then as you see, the leftmost child, 1621, and that actually needs to be somehow connected with this now sort of floating child that we have not attached because this operation. So what we do is we actually just move that the smallest value of the right child into the parent. To replace that, we pull down 11, and then we delete 6. Okay. So what if we're gonna want to delete 11? So we do this similarly, and we're gonna move this 21. Well, in this case, we can't just we want to, if we move this 21 to the parent, we can't do it because this is becoming empty. So when it becomes so low, it has only one value left, one key left, we merge with this node. This is the other case. And then we delete 11. See that? So this is the couple of variations of the sort of the trickier situation when you delete, when sort of it becomes underflow condition. Let's say you delete a bunch more, and now we have this, we're left with this tree. Now, let's say we want to delete 31, and Okay, we'll do a similar thing. We'll pull that parent value down, 36. Now this node becomes empty, and then we're going to do. So what we're going to do is, well, first of all, just remember what I have to do is, first of all, this needs to be combined with the other the other child, and this. But remember, this parent is still empty. We have to do something about it. Okay, well now we delete the 31 can be deleted now. This is what we want to delete to start with. But we have to deal with the parent. And the parent, what we're going to do, so in this case, we can move down the root. We can move down the root into that position. If the root also underflows, becomes empty. And this is the case where the tree's height reduces by 1. What we do is we need to merge this with the other child. Becomes 46, 56, and that becomes a 1 node. And then that original root node will be deleted. So as you see, the tree height is decreased by 1 because deletion in this case. This is a little bit of a trickier situation here. So deleting from a B tree, you know, just in summary, if it's not a leaf node, we simply replace the key with a successor from a leaf, and then delete out of a leaf. Now, if we're deleting a node from the key from a node, if the node has more than b minus 1 keys, right? Essentially, we still have enough keys to delete, so we don't have to do any changes. And then you simply just delete the key. Otherwise, we'll have to find a sibling node whose shared parent is p. And this is describing what we're just talking about in the example. If that sibling has at least b minus 1 keys, then move the maximum min key from that sibling into p's place. Okay, and then move p down into the current node, and then remove that key. And then we may also want to fuse or merge that node with a sibling to a single node by adding the parent p into the block. And then we do that recursively. So we already had kind of look at the example how it's done. This is a summary of this algorithm, how we're deleting. And so it turns out the deletion complexity also is a big O over log of n, which is pretty efficient deletion as well in B tree. So what's the connection with the red black trees? I already said the 2, 3, 4 tree. We'll see. Now the red black tree is a BST with the following properties, right? Just to review, and we have every node is either red or black. The root is black, and then if you have a red node, it cannot have the red children. Okay, and then of course every path from the root to null, you have the same number of black nodes, 2 nodes, 2 black nodes, and 2 black nodes, right? And what we can do is we can morph it or transform it into sort of a multi-way nodes, search tree, like a B tree, essentially. As you see, what we do is think of a black nodes as a primary nodes, and then red nodes as auxiliary nodes or secondary nodes. And what we do is we sort of collapse. When you see a black node, that stays in its place, but we're going to collapse a red node, a nearby red child, into that node, and you do that for every black node. So, for example, 166, you collapse this into 110. Now, this is how we view it, and it just help us understand. We're gonna kind of study the red black tree from a B tree angle. So you see, you put this 166, 110 together. You put this 106 and 107 together. Now remember, when you put in a node, the keys are still ordered in that fashion. Remember, it has to be ordered. And then this 146, 140 goes to the 161, as you see, and this 261 doesn't change. You see this? It becomes this condensed B tree, essentially. And here's another example, same thing, and this is black, and then this red just goes into that, and this stays, and these 2 red children goes together into this one single node. So you have 11, 13, 17. Same thing here. These two red nodes will be in the black node. We'll collapse them. So you see, it becomes this condensed B tree in that way. So what we're doing is we're saying structurally, we can think of red-black trees as 2, 3, 4 trees. And they are sort of a structurally equivalent. And we can study red-black trees basically by virtue of a B tree, essentially. And then we know B tree is easier to reason about, and there's only very few cases when it comes to insert and delete operations. But if you just study the red-black trees alone, there's many cases to consider and change the tree in this way and that way. So this is kind of just the alternative interpretation of red-black trees by virtue of using a B tree here. So that's what we're talking about here. So we'll see. Now the height of a red-black tree, of course, it's a big O of log of n, and we have seen this before. Now you can reason about this height by using this 2, 3, 4 tree, and which is, we know the height of that B tree, and so the original red-black tree, essentially can be bounded by that big O of log of n as well. So let's take a look at this sort of isometry, the sort of a structural equivalence between these two types of data structures. And the nodes, 2 through 4 tree, as we explained, you have 2 nodes, 3 nodes, 4 nodes. This number represents the number of children that node can have. So now how do we compare this with red-black trees? If you have a node that has a 1 key, this is a black node. Now, if you have a node that has 2 keys, now one of them is black, the other one is red. So it could be this or this, right? So you have a red as a child. Now remember, we're always collapsing a red into the black. So this red node, red key could be greater than the black or less than the black. Now, if you have 3 keys in this node, then the black node must be in the middle as the parent, because imagine if this is red, you don't do that, right? Because again, just a simple rule here, we only collapse the red nodes into black, okay? So let's use this isometry to, again, so how do we, this is an example, red-black tree, and then we'll collapse the red into the black, as you see here, this 3, this goes here, this goes here, this goes here, and so it becomes this, okay? Now, let's say we want to insert a key 5. To insert a key 5, we know this is a place we're going to insert. And we don't know the color yet, so we just label this as blue. And now, because the color, we have to maintain that color constraints, right? Every path from root to null has to have the same number of black nodes. Now it's let's say how we're going to do this. So basically here, there's some simple rules we can follow. If we're going to put this into this black node, this has to be a red one, right? Because we don't put black and black in a single node. The blacks, stay as a single node on its own, and only the red nodes will be collapsed with the blacks. So 5 will be a red. Now here's another example. Let's collapse this into a B tree. And then now we want to insert 37. Now 37 we insert here, and this is on this leaf node here in the B tree, the equivalent 2, 3, 4 tree. Again, we have a black in the middle and we're red. So we see the situation when it comes to this node that has 3 keys, and then the left and the right, they must be red, right? So where to know this? By that simple virtue of analyzing the tiny structures, it's very simple to do and to actually know the color of that node, of that key, by the way. So here's another example, right? Okay, so this is actually, well, this is showing you after we have done this operation, then we're gonna revert it back to the red black tree. So it will be like this, okay, right? Put it back. You see the process. It's the same, the reverse of what we did to turn this into a 2, 3, 4 tree. So the rule number 1 is when you're inserting a node, if its parent is black, will simply make the node red and then stop. It's very simple. So we are essentially simulating, let's say the blue is what we want to insert. We start with, let's say you have a 2 node. Okay, this one block is a 2 node. Remember, 2 node means 2 children, 1 key. So this will be red. We'll just turn this red and then stop. And if it's a 3 node, we have basically 2 keys here. This is what we have currently in this way. And then we put this thing here on the left, and then turn this red, and we're done. And then if the red is the smaller value, and then this new key will be bigger value and put into the same node, and this will be red as well. So let's say another example, we change this into 2, 3, 4 tree. Now we want to insert 4, right? So I want to insert 4, and then in between 3 and 5. So now we know this should not exist, and the 4 should be black and the 3 should be red. So somebody just change that, right? So very simple. And then we'll basically we'll turn this back into the red black tree. See, this will be like this, right? So we just need to change the colors of the nodes and move the nodes around the tree. Now, when it comes to inserting, like when we get to the sort of overflow, underflow situation, when we study the B tree, right? And the typical operations that we have to do to rebalance the tree will be to rotate the tree. And this is what we kind of very simple abstraction of this tree, where we have, this is a subtree, this is whatever is underneath. We're dealing with the A and B here. To rotate this right, we'll say this operation rotate 3 rotations. To rotate this right, we make A the parent and B the child. And then this whole child tree goes along with it, right? You see, this is the rotation. But this purple color subtree, now it becomes the child of a B now, okay? See, this is the rotate right. And the opposite is the rotate left. If you start with this format, you want to rotate left, and then you turn B into the parent, A into the child, and then the B's left child becomes A's right child, okay? This is the sort of a basic operation that we're gonna need. Now, the tree rotations are fundamental primitives in binary search tree. And they are, this essentially was making it possible to reorder the nodes to preserve the binary tree property. And most binary trees are going to use tree rotation at some point, okay? And so here's some example here, right? We'll look at, let's say this is the tree you have, and we want to use, let's say want to insert a key value 4, right? Now, to insert the 4 here, and we have to do some rotation. We rotate, we're gonna rotate this first. We're gonna rotate right. You know, we're gonna turn 4 into the parent, 5, 5 into the child, with the children if we have them. But here we're not necessarily showing here. And then once it's here, and it's not enough, we have to balance this by rotating again to the left. So essentially 4 becomes parent, 3 becomes the 3 becomes the child, okay? Now, once we get to this particular shape, and then we just need to change colors, and the 4 has to be black and the other 2 are red, okay? So this is how we can rearrange the structure to maintain that property. So here's an example. This is a red black tree. We're inserting this key 4. So we rotate to the right like this, and then rotate to the left like this, and then we fix the colors, right? You see, so it still maintains that the number of black nodes on any path, right? 2, 2, and 2, right? Now let's say we want to insert 15. Okay, same thing. We're going to rotate to the right and then rotate to the left, and then we fix the colors. 15 is black. See, 2 blacks, 2 blacks, and 2 blacks. Okay. Now we turn this into a 2 through 4 tree. Let's say we want to insert 16. Okay. See, we're going to insert 16 into this node right here. So what we do is we just essentially, remember what we did with the B tree operation. It overflows, right? We cannot have the 4 keys in any node that's already exceeding. So we split. We'll pull out the sort of the maximum value of the first block. As I mentioned in that algorithm, we could also potentially use the minimum value of the second block. But again, just for consistency, we're going to use this. And that becomes the new parent. And that will be where you have to push this into the top, the original parent, essentially. It goes in there. Now, once it goes in there, though, we have to fix the coloring. Now, remember, whenever you have a set of 3 keys in a node, the middle node has to be black and the other 2 are red, right? See, it'll be like this. So as you see, by changing this into 2 through 4 tree, and the red-black tree operation becomes pretty straightforward now. Now, I'm going to skip this for now. So here's another example. Okay, okay, let's see what we're doing here. So let's say we actually insert in 16. Okay. We need to rotate this the 15 that was pulled out, and then with its parent, and then rotate again, and becomes a balance. See, what the rotation really is about balancing the trees. As you see, we have to do a rotation so that we can get the equal number of black nodes on every path to maintain that property of red-black trees. So by doing the rotation, you see what's happening is we are making the tree, turning the tree balanced again, like this. And so that's really what that is about. And then fixing the color is fairly straightforward. And so that's really the gist of that. So here's the thing. As you see, the red-black tree operations, if you just look at that alone without the help of the 2, 3, 4 trees, it can be a little bit crazy. There's a lot of cases to handle. And by using 2, 3, 4 trees, we kind of really simplify the operations of red-black trees. And this tree, the red-black tree, and also the B trees, they are very efficient trees for the insertion deletion operations. They're all just a logarithm complexity. So these are actually fairly common data structures that you're going to see used in different places. The implementation of these 2 data structures are a little bit involved. You can certainly find all kinds of implementation out there if you want to study that. And of course, the battle tested real world, application may have a lot more involved stuff in it. But at least you should understand how these data structures work, and be able to visualize how the operations are going to change the structure, and then keep the, one of the key things is to maintain the property of the data structure. That maintaining the property of data structure is the same regardless of what data structure we're looking at, linked list or whatever, right? You remove a node, you have to keep attach the 2 sections, put it back into a single linked list, right? So that's the invariant. You always, after every operation, if it's a mutation operation like deletion or insertion, you always want to keep the data structure valid. It's still, whatever the original properties it's defined that data structure, they have to be maintained. Otherwise, you have no more basis to operate on. This data structure. It just becomes a random thing. So that's one of the key thing here. So as you see here, we'll just kind of introduce a couple of more different kinds of trees. And trees are very useful in many different applications in your programming life. You're going to use all kinds of trees, and either some implemented by somebody else, or you may have to implement your own at some point. Um, so just to want to expose, you guys to a couple more data structures that are in the tree category. Okay, so that's what I have for today. Yeah, that's what I have today. Okay, so I'll stop the recording.